Welcome guys. So in this video, we are trying to start in our global geometry application. So this probably is the shortest video of this section. So we prove this fact that the regular compact surface S is a subset of R3 has at least one elliptic point. Oh, so what it says is basically if you have a you have a surface S in R3, then S must has a point which Gaussian curvature is greater than 0. This is somehow like the very intuitive. I mean, if you think that suppose if you try to have a space, right, which every point has the Gaussian curvature negative, then it seems like that this surface will extend to infinity, right? Because at each point of the surface, it looks like its Gaussian curvature is negative, so it's like the concave one, right? But for S, so the intuition tell you that if you have a surface which every point has Gaussian curvature negative, then it will extend to infinity. So conversely, so if you flip this statement, then you will get the regular compact surface as subset of R3 has at least one elliptic point. So this is the same as the S must has one point which Gaussian curvature is greater than 0. And why I say this video will be very short, because the proof is very interesting. Okay, so the proof. Okay, the proof is very interesting because we know that S is compact, right, and regular. So S is here. Sorry, let's say S is here. So I can so people can what? People can just draw a large sphere. People can just draw a very large at some origin and choose a large sphere which encloses this S. So this is a sphere. Okay, then one can just take this one can just shrink this sphere, right? Shrink this sphere. And at some point, right? At some point that this sphere will meet with S. So let's say this point is P. So that means if, right. But that point, right? That point on the sphere has the Gaussian curvature positive. So it's 1 over, let's say this is R, right? 1 over R squared, which is greater than 0. So at least. So that means P has Gaussian curvature greater than 0. So that means S has at least a point, because we already proved P has, right? So this is the proof. So done. So this proof is very interesting because, I mean, so ideally it looks like very difficult that so intuitively this is correct, but how do we prove it? So we prove it by very natural way. Just pick a large enough sphere and shrink the sphere, and the sphere will meet the surface at some point. At that point, will just satisfy our criteria. Okay, so that's for today's video, and I will see you guys in the next videos.